Hi there, Dr. P here, and in this video, I'm going to talk about resonance structures. So let's go ahead and get started. Okay, let me just adjust my camera here. And we can go ahead and get started. So Chapter 2, Lecture 2. Now, resonance structures, as I've mentioned before, are alternative Lewis structures that are also valid. So alternative valid Lewis structures. For example, we could have benzene, we could have, let me write benzene in here. We could have the acetate ion. And there, of course, are plenty of others. One thing to note is that if we look at some features here, we have a resonance arrow. Which is this double-headed arrow or double-ended arrow. This is not an equilibrium arrow. It's not a reaction arrow. It's not a curved arrow for drawing mechanisms showing where electrons go in mechanisms. It is a resonance arrow. You only draw it in between resonance structures. We also put our resonance structures in brackets. To indicate that these structures are equivalent structures for a given compound. Now we have some rules that we need to be aware of. The first thing is that we can only move electrons. We're not allowed to move atoms. And the electrons can only be from multiple bonds or lone pairs. So we're not going to break any single bonds. We're not going to break any single bonds. Another way of saying this is that we are going to pretend that the atoms are fixed on the page or on the board or whatever. So we're going to pretend that our atoms are fixed. And then what we want to do is consider relative stability of the different resonance structures. And if we have a complete octet, so go back to drawing Lewis structures, if we have a complete octet, that's going to be more stable. We'll say complete octet equals more stable. We'll do these bullet points here. Fewer formal charge equals more stable. And I don't mean fewer total formal charge or total fewer net formal charge. I mean total number of formal charges. We also have more stable resonance structures when negative charges are on more electronegative atoms. And then conversely, positive charges on less electronegative atoms will be more stable. And you can think of that just when you think of what electronegativity means. It's the tendency for an atom to pull electron density onto itself when it's in a covalently bonded compound. So we have a full negative charge that's going to be happier, quote unquote happier, on an electronegative atom than it is on a less electronegative atom. So negative oxygen will be more stable than a negative carbon. Also, less charge separation less charge separation will be more stable as well. Okay, now, one thing that I haven't really mentioned here was formal charge. Now, you may have done this. Hopefully you did this in Chem 1A. If not, well, this is a great review. So let's take a look at formal charge. Formal charge is simply the difference between the number of assigned electrons and the number of valence electrons for an atom. If you think back to Chem 1A, you probably looked at oxidation numbers, Chem 1B as well. You probably looked at oxidation numbers. That's a way of keeping track of electrons, sort of electron bookkeeping, if you will. Formal charges are a similar idea, but for organic molecules. So if we look at an example here, of methoxy, we can see that we have each hydrogen has one electron assigned to it because we just have one bond. So we consider the bond single bonds, we're going to split those electrons 50-50. Even though they're polar covalent most of the time, we're still going to say that let's arbitrarily assign one electron to hydrogen and then one electron from that bond to carbon. So you would simply count the number of bonds that are attached to an element, and that gives you the number of electrons assigned to it. You also have to include lone pairs. So each hydrogen has one electron. Now, normally a hydrogen has one valence electron. So these hydrogens all have 0 formal charge. Carbon normally has 4 valence electrons. Here it's being assigned 1, 2, 3, 4. So again, 4 minus 4 is 0. So again, the carbon is also 0 formal charge. Oxygen, however, is going to have 1, 2, 3, 4, 5, 6, 7 assigned electrons and 6 valence electrons. Which 6 minus 7 gives us -1 formal charge. So there's my negative formal charge there. A lot of times we'll just write this as CH3O minus, like so. We could use this to figure out, I don't know, a molecule like the following. What are my formal charges? Well, I haven't drawn a full Lewis structure here, but that's okay, because I know each carbon is attached to 3 hydrogens and then the central carbon. So that's 3 bonds with hydrogens and 1 with carbons. That's 4 bonds for electrons assigned 4 valence electrons, so 0 formal charge. Each hydrogen has 1 assigned electron, 1 valence electron, 0 formal charge. In the middle, this carbon has 3 assigned. Normally, it would have 4 valence electrons. So this has a plus formal charge. Okay, 4 minus 3 gives us 1. That's our formal charge. Now we can use this when we look at resonance structures. Now, we can't always draw resonance structures for a given molecule. We usually have to have lone pairs and or double bonds, multiple bonds. So let's see, can we do this here? Well, actually we can. I could, with my red arrow here, draw. So this arrow equals 1 pair of electrons. And so now I'm going to have, again, all my atoms are being held in place, I'm pretending. Now I took a pair of electrons and pushed it onto that carbon, the right-hand carbon. So now my left-hand carbon only has 3 electrons assigned to it, so it's 1 short compared to valence, so that has a positive charge. The one on the right has 1, 2, 3, 4, 5 assigned carbons, so that would be a negative charge. Now, we may want to evaluate these resonance structures. Not all resonance structures are equally important. In this case, we would say that the structure on the left here is the major structure, and this one is the minor structure. Why would it be minor? Well, it has formal charges. It has charge separation, and also one carbon has an incomplete octet. So if we go back and take a look at our rules for resonance structures, we want to consider our relative stabilities of our different resonance structures. So complete octet is more stable. Incomplete octet on the right-hand structure. So it's going to be less stable than this one. And then we've got charge separation, and we've got formal charges. Although they add up to 0, we still have 2 individual formal charges. So that is not as good a resonance structure. Okay. Let's take a look at some other examples here. And let me write these down. Draw resonance structures for each of the following. So let's do HCN as 1. And let's see here. Let's do that guy there. And then maybe one more. And do H2CO. Okay. So the first thing to do is to actually draw out a reasonable Lewis structure. Carbon's going to be in the middle because it's the least electronegative. It likes to form 4 bonds. Only one will be to a hydrogen. The other 3 are going to be to nitrogen. Now our nitrogen is happy too because it likes to have 3 bonds. I can go ahead and push electrons onto the nitrogen. And now I get HC double bond N. There's a negative charge on the nitrogen, positive charge on the carbon. I could push more electrons onto the nitrogen and get HCN with the 2 minus charge and the 2 plus charge on the, I'll circle those, 2 plus charge on the carbon, 2 minus charge on the nitrogen. So of these, the first one is going to be major because it has complete octets, no formal charges, no charge separation. The next one will be minor. And then the last one we would say is very minor. Okay. So let's take a look at the next one here. And I've drawn the bond line structure. Go ahead and let me actually, I'll draw out the Lewis structure here. Okay, so this is my Lewis structure. And at this stage, it might be easier for you to work with Lewis structures showing your hydrogens. It can take a little getting used to recognizing where the implied hydrogens are. This one, I'm going to just use my bond line structure because I know what I'm doing. So I could have a pair of electrons here from this double bond move over, and so that bond is still in the same place. That guy's there, and now my positive charge is going to be there. And if you're having trouble following along with this, go ahead and draw out the Lewis structure, and then you can go ahead and draw your arrows pushing electrons, and you'll see maybe a little more clearly if you're having trouble. You'll be able to see where the positive charges are. Okay, now I could have gone the other way, so I'll just go back. I'll push those electrons back, and then I'll push those electrons over. And notice that my arrows are starting with a pair of electrons and ending at a bond or at an atom. So your arrows are always going to start with a pair of electrons, either from bond or lone pair, and they're going to end at a bond or an atom. At any rate, I'll now have those there and a positive charge there. Now, I could do some weird stuff, like I could have those electrons go there and then get positive charge there, lone pair, negative charge, positive charge there. But long story short, these three are the major three. And these others are going to be minor because they all have additional charge separation. A lot of times, well, maybe most of the time, we don't even bother drawing in the minor ones. So for example, for drawing HCN, we're not going to draw the minor and very minor resonance structures. For drawing C2H4 ethylene, we're not going to draw this minor structure. The time when we do draw a minor resonance structure is when it is needed to explain stability or reactivity. So let's look at our H2CO here. Carbon's going to be in the middle, and it likes to form 4 bonds. So let's do that. And then my oxygen is going to have 2 lone pairs there in addition to the 2 bonds. Now, I could push electrons. Now I'll have a negative formal charge on the oxygen and a positive formal charge on the carbon. We would say that the structure without those charges is major and the other one is minor. But we still may want to draw this, or at least have it in the back of our mind, because in reality, what this is saying is this resonance structure is explaining the same thing that this diagram with the partial charges is explaining. That in reality, we don't have just a fixed formaldehyde here with evenly distributed electrons. In reality, the electron density is more on the oxygen. It's a minor resonance structure, so it's not as heavily weighted in the picture of reality. We could draw it like this if we want to. I mean, I just look at carbonyls and think, oh yeah, that's polar, partial positive charge on the carbon. That's just what I think. But then again, I've been doing chemistry for 2/3 of my life. So, gosh, more than 2/3 of my life. Anyway, we can use resonance structures to explain stability and reactivity. So an example like benzene, the resonance structure helps explain why benzene is so stable. In the case of formaldehyde and other carbonyls, the resonance structure helps explain why they react the way they do. If you bring a certain type of molecule called a nucleophile in, the nucleophile is going to add to the carbon of the carbonyl, not the oxygen. That's because nucleophiles are electron rich, and this carbon here is electron poor. So drawing these resonance structures can help us understand how certain things react. Now, the last thing that I want to do for this lecture is to ask the following question, give you guys a little bit of practice here. And of course, we'll do more practice in person. And let's ask the question, what is wrong with the following resonance structures? Okay. So, and maybe I should just say, yeah, I'll say resonance structures. What's wrong with it? Well, what's happening here is we are moving hydrogens. So I'm going to draw in the hydrogens. What's our problem here? Well, notice that I have two hydrogens on this lower carbon here. And in my quote unquote resonance structure, I only have one. And I have two hydrogens on this top double bonded carbon. And in the quote unquote resonance structure, I have three. So I have moved a hydrogen. And that is bad for resonance structures. You're not allowed to move atoms. Now, what would a valid resonance structure look like? Well, I'll go ahead and grab my red pen here and push some electrons around. So if I push these electrons around there, I'm going to have to push these electrons around because I can't have 5 bonds on carbon. And they're going to have to go onto that carbon. They can't go to make a new double bond because then I'd have 5 bonds on that carbon. I have 1, 2, 3, and then the double bond would be 4 and 5. So what I end up getting now is the following. I have a positive charge up there. I've got a double bond there. And then I've got a lone pair and negative charge on that carbon. So this would be a valid resonance structure for the first structure that I drew. Notice that it is very different, but all we did was push electrons around. So there are some practice problems you can work on. And drawing resonance structures is important because, again, it can help us figure out stability and reactivity. And in the next lectures for this chapter, we'll look at acids and bases and acid and base strength. And one of the factors that we might have to consider is resonance. All right. So until then, you guys stay safe out there, and I'll see you next time.